Hello, everyone. Today, let's talk about chemical kinetics. So, why do we need to talk about chemical kinetics? Well, as you can see, the reaction can be thermodynamically favored, while the delta G can be very negative, but it doesn't mean that the reaction has a high rate of reaction. The reaction can still have a very, very low reaction rate. Well, a reaction, one mole of reaction might take hundreds, thousands of years. So that's why we need to care about the rate of a chemical reaction. So let's take a look at example here. Well, if there's a reaction, A moles of A plus B moles of B, which forms C moles of C plus D moles of D. The rate of reaction, we know the rate of something is just the rate of change of something divided by, the change of something divided by changing time. And in this case, the average rate of the reaction is -1 over A, small a, the coefficient of A, times delta A over delta T, which is equal to delta 1 over B times delta B over delta T, which is also equal to 1 over C times delta C over delta T, and which is equal to 1 over D times delta D over delta T. As you can see, in this case, we divide by each term by its own coefficient, and that's because the different coefficients will affect. We got different value of this change in changing reactants or changing products over changing time. Right, this value and that value can be different because they have different coefficient. The rate of change of them can be different. But as you can see, if we divide it by the coefficient for each matter, for each substance, well, they can be the same. And we want the rate to be positive because the rate of change of reactants is negative. That means we need to add a negative sign in front of them to make them positive. So let's take a look at like an example here. We have 2 moles of N2O5. It decomposes to form 4 moles of NO2 plus 1 moles of oxygen gas. So we need to calculate the average rate from, well, as you can see in the table, from t equal to 100 seconds to t equal to 400 seconds. So let's do this. The average rate is -1 over the coefficient, which is 2 here, times the change in the concentration of reactants. Well, the concentration 400 seconds is 0.0101 moles per liter, minus at 100 seconds is 0.0169 moles per liter, divided by 400 minus 100 is 300 seconds. So let's plug in this into a calculator. Well, the value is 1.10 because we have 3 significant figures, times 10 to negative fifth. I think 10 to negative fifth. Okay, let me check again with a calculator here. Okay, is 1.10 times 10 to negative fifth. Remember, the unit is molarity per second. Well, we have known the average rate of the reaction. Let's talk about rate laws now. Before we talk about rate laws, we need to know what is the law of mass action. So, the law of mass action tells you that the rate of the reaction is directly proportional to the concentration of reactants. And that's easy to understand because we know the chemical reaction basically is a result of the collision between the reactants. The reactant is those small particles here, right? The small molecules here. And chemical reaction happens because they collide to each other, right? So if you have a pretty high concentration, that means the chance of getting collide to each other is pretty high. So the rate law of the same reaction here is just equal to, well, the rate law is also called rate equation. It tells you that the rate is equal to some constant, we call rate constant K, times the concentration of the first reactance A to the nth power times the concentration of B to the nth power. What are M and N? M and N are the exponents. They are some constants, and they are determined by experiment, typically. The reaction order, in this case, is determined by M plus N, right? If M is 1 and N is 1, well, 1 plus 1 is 2, so this is a second order reaction. If M is 1 but N is 0, well, that's 1 plus 0, which is a first order reaction. If M is 2 but N is 1, that's 2 plus 1. 2 plus 1 is 3, so that's a third order reaction. Well, we have an example here, and we also have a table to show different trials. As you can see, trial 1 and trial 2 has the same concentration of hydrogen gas, but different concentration of nitric oxide. And trial 2 and trial 3, they have same concentration of NO, but different concentration of H2. And the initial rate of each trial is given. So let's determine the rate law of this reaction. Well, in the first trial and the second trial, we increase the concentration of nitric oxide by a factor of 2. We times 2, we double it. And as you can see, initial rate quadruple, right? Times 4, because 5 is equal to 4 times 1.25. We know we know 2 to the second power, 2 squared, is equal to 4. That means the exponent for the NO is 2. So the rate is equal to K times concentration of NO to the second power. Well, if you compare second and the third trial, as you can see, we don't change the concentration of NO, but we change the concentration of H2. Well, when we double the concentration of H2, we also double the concentration, the initial rate. That means because 2 to the first power equal to 2, so the exponent for H2 is just 1. So the rate law is K times NO to the concentration of NO squared times the concentration of H2. And as you can see, in this case, the exponent for NO is 2, exponent for H2 is 1, so 2 plus 1 is 3, so this is a third order reaction. Okay, so previously we talked about instantaneous rate, but we talked about average rate, and so now we need to talk about instantaneous rate. Because most of the time we know that the rate of reaction is not constant. It will change with the concentration of the reactants. So what we do here is we make delta t approaches 0 to make delta t pretty small. We can't make delta t equal 0. If it equals 0, because we know the denominator cannot be 0. But we can make it approaches 0. So as you can see, delta A over delta T, as delta T approaches is what? Is just the derivative of the concentration of A with respect to time. So the instantaneous rate of a reaction is just -1 over A times the derivative of A with respect to time. And the following, you just change the delta and delta to D and D, to the derivatives. So since we have learned rate law also determines the rate of reaction. That means we can make these two things equal to each other, and that's called a differential rate law because we have derivatives here. All right, but as you can see, this expression here, it does not directly show you the relation between the concentration of reactants and time. So what we do here is that we need to get an integrated form of the rate law. Well, how to do it? Well, we will see that in the next video. Thanks for watching.